Hello, welcome to the Critical Materials Innovation Hub webinar series designed for CMI and by CMI. I'm Cynthia Howell and I'm going to be your moderator today, and I work in CMI as the Education Workforce Development Manager. I'd like to tell you a little bit about the webinar today. And if we can, webinars are hosted by Colorado School of Mines. If you have a suggestion for a future webinar, we're always looking for topics to serve you. That's what this is designed for. Please make sure that you have it on the exit survey or email at cmi@mines.edu. This is a public webinar, so recording's going to be available next week. It'll be at ameslab.gov/CMI under the webinar tab and or on our YouTube channel. Questions. We're going to hold all the questions to the end of the presentation, but when you have that question, I encourage you to type it into the Q&A box, so it'll be in the queue and ready to go when questions are available. They're going to be again answered at the very end of the presentation. I'd like to introduce our presenter today. So today we have Dr. Jun Cui, a faculty scientist at the Critical Materials Division at Ames National Laboratory. And he, prior to coming to Ames, he had his postdoc at the University of Maryland and also his PhD from the University of Minnesota. Prior to that, also, he worked with GE Global Research Center and also Pacific Northwest National Laboratory. And that was all before he joined us at Iowa State and Ames National Laboratory. And I don't want to take any more of his time. Dr. Cui, if you'd like to take over from here.
Thank you. Cynthia, can you hear me well?
Yes, very good.
Good. So today, this is Jun. I'm going to talk about the hydro nanocrystalline anisotropic neomagnet. This is a teamwork with several scientists here at Ames Lab, as well as several scientists at the Livermore. Many names here, so I won't read them all. So this work, so far, I think it has been supported by the CMI Hub for at least 3 years by now. So a lot of progress has been made, and of course, a lot of headache and problem that is still waiting us to solve. So a little background why we're working on nanograin magnet is all coming to the criticality of the materials. So one of the most studied critical material is this rare earth neodymium and the dysprosium. So both are the elements for permanent magnet. So there was a study about this demand and supply. They all pointed to a significant shortage and supply risk for both material as soon as in 2030, especially the dysprosium because it's scarcity. So this slide just show a geological survey of the abundance of those elements in US. So there are 3 minerals that we're looking at here on this table. Basanite, that's in California, that what we have in the United States, and then monazite in Australia, and then denopime in Malaysia. So if you look at them, see if you can the laser. So Cynthia, can you see my laser? All right, I guess you can. So if you look at the table of contents.
Yes, we can see it.
All right, if you look at the table of content, actually it's not bad. The amount of neodymium and praseodymium that we have here in the United States is 13% neo, 14.4 of praseodymium. If we sum these two things together, we have roughly about 18% of usable rare earths for making magnet. But we do not have heavy rare earths, or especially terbium, dysprosium that commonly used in permanent magnet. It's not like completely zero, but it's less than 0.1. So this is a significant shortcoming of the minerals that we have in the United States, and we need a solution to address this. So now, a step back. So why do we need a rare earth permanent magnet? So one of the major driver for this demand is the EV, electric vehicle motor used in the electric vehicles. So motor actually can run without permanent magnets. So you can just put a copper bar in a cage, and then you energize it with electric current. You can generate your own magnetic field. But those excitation cause you extra current, extra energy, extra electricity, and typically the difference between the permanent magnet powered motor versus the induction only motor, the one that without any permanent magnet, the difference is roughly about 10% efficiency. It's quite intuitive in a way that permanent magnet bring your own magnetic field, while induction motor don't. You have to generate yourself, and it costs energy to generate that. So the efficiency difference between the induction one and permanent magnet one are getting shrinking down as low as at 7-8% when your RPM getting high, as high as 10-15,000 RPMs. So permanent magnet is expensive. So this chart show almost half of your motor cost is because of the permanent magnet is more expensive than the induction motor. But yet at system level, although your motor is more expensive, but you are more efficient and you use less electricity, and therefore you can save battery cost, or with the same battery, you can have a longer driving range. So that's the philosophy. You don't look only at the motor level, you look at the whole system solution and see what the overall cost. This is why permanent magnet is needed and preferred. So for motor, for EV, they're running hot. The temperature can be as high as 180 degrees C. And unfortunately, magnetism is an ordering behavior. With temperature rising up, atoms vibrate more, and you start to lose your magnetism. And you certainly start to lose your ability to resist the demagnetization field. So one solution to maintain your magnet's magnetization at higher temperature, the coercivity, is to add in heavy rare earths. Fundamental reason is, for example, heavy rare earths, dysprosium 214-1 is anisotropic field is much higher than the neodymium-iron-boron. Adding in can help you stabilize your magnetic structure under high temperature. This chart just shows that this red line, that's the one containing dysprosium, versus the one that does not. So see, if you want to maintain the same coercivity, by adding dysprosium, you can gain almost like 70 degrees C. That means adding in dysprosium can help magnet to maintain this magnetization 70 degrees higher. So on the right, it shows how much dysprosium do you need to maintain those magnets property. Here is a 2012, almost 12 years old article, is referring to the magnet that with heavy rare earths inside of the grain. So this is a classic method of making magnet. It says if you want to run at 180 degrees C, you will need 6 to 8% of dysprosium. So, and then I think a few years later than that, and a group of scientists in Japan pointed out if you diffuse heavy rare earths along its grain boundary and only leave those heavy rare earths in grain boundary, you can be just as effective as you leave the dysprosium in the main grain. So if you're using the diffusion, grain boundary diffusion method, and then to maintain the same high temperature performance, the amount of dysprosium is dramatically reduced from 6 to 8% to 2 to 4%. So you only use about 20 to 30% of what you have to do. So that was a very good development, a great save for the heavy rare earths. But it's still not widely used nowadays. The main reason is it takes time, it takes cost to make the heavy rare earths diffuse over grain boundary. So there is a cost for saving the heavy rare earths, unless this cost of saving rare earths is more than the cost of the heavy rare earths. Otherwise, those methods will not be used. This is why there's still a lot of places people still stick to this traditional rare earths, heavy rare earths in the coin magnet. So now let's talk about nanograin approach, why we think it's a good way to solve this heavy rare earths. So it's a little bit the busy chart. So let's look at the table first. So we have A, B, C, D, E, 5 compositions, and they are grouped into 2 categories. One is dysprosium limb, we'll say no dysprosium, 0 dysprosium, A, B, C. And then you have B and E, which containing 1% dysprosium and then 2% dysprosium. So now, if you look at 180 degrees C, with higher temperature, the coercivity wise, of course, E, that's the one with 2% dysprosium, give you the best performance. So as you see, the coercivity is getting higher and higher with the grain size getting smaller. And then if you look at the D as in dog, so the dysprosium amount is about 1%. So it's also increasing and maintaining a decent level. You at the grain size about 200 nanometer. But then now, the most interesting one is C, this composition C as in Charlie. So composition C has 0 dysprosium, but yet if you maintain a smaller or comparable grain size, you'll see what is the coercivity. It can offer the coercivity as high as what you have with a 1% dysprosium. So this is just to directly show that you can, using nanograin approach, make a fine grain magnet, and its coercivity can be comparable to the one containing 1% of heavy rare earth at 180 degrees C. On the right is show the temperature coefficients. This is the beta. That's for the coercivity. It shows the dysprosium one, heavy dysprosium one is the best. And then this one, interesting, this C, composition C, actually offers even better coefficients than the one containing 1% of dysprosium. So this is the published data by Keiko from Daido. Daido is a company known for making their nanograin neomagnet. So this is the established knowledge. So now let's look at how do they make them. So nano neomagnet is higher performance, it containing less heavy rare earths. Of course, it's expensive. So here's why it's expensive. First, you start with melt spinning powder. The powder has to be nanograin, 20 to 30 nanometer. And then you pack them as dense as possible, although you want to make them fully dense, but the chances are there's still some porosity. Perhaps 60–70% dense is what you can achieve at room temperature. But nonetheless, you want to try everything you can to make them really dense. And then you heat it up. You plastically deform them. This is the part that where you want to plastically deform them, and you want to borrow temperature to help you to achieve those plastic deformation, but yet you don't want the temperature too high. You don't want the grain to grow out of control. And you, as a matter of fact, you don't want any grain to grow. So this is a part that you typically want to control the temperature to be less than 600, 650 at its best, maybe 680 C. So this is the part you can achieve a fully dense pre-packed magnet. So actually, this is the part that in most of cases is already a magnet, right? So, but now what you have to do to truly get the high texture of this proven magnet, what you have to do is you have to de-dye them, take it out, and then put them into a new dye. This one is a backward extrusion. So you press, you plunge in, and then your pre-dense, pre-consolidated puck going to be backward extruded and give you a ring product. Or you load it into forward extrusion die where you can press from backward, and then it will give you a rod or rectangular bar products. So the later part, this hot press part, is essentially a grain growth process under the bias of stress. So it turned out the nanograin, is actually T structure, right? It's a tetragonal structure. So it turned out you prefer to grow along its C-axis and the stress. So if you press them in this way, extrude them this way, so you will get the ring, and then with a texture perpendicular to the stress direction. And this is the stage where you want enough temperature for grain to grow under the bias of stress. And you want it to grow just enough to give you the texture, but never grow too big. If your grain grow too big, you lost all your coercivity. So this is a careful balance between the stress, temperature, and time. So it was a pretty tedious process to do that, and plus the heating, cooling, de-dye process all have a minimum requirement of temperature and time for you to complete all this process. So the green size that you can obtain with maximum texture is also limited. So we have two issues here. One is cost, one is performance. So this is what the traditional do: melt spin, cold packing, hot press, and then extrusion. So now the process that we develop here at the CMI is we pack the whole thing in a tube, and then we pre-pack them into a near fully dense at price 60%, and then we go through a series of a hot roll process. So we heat it up with induction heating. So this is much better than the furnace one because we can heat up very fast. And then we cold roll them. When we do the cold rolling, it's not cold roll. Our tube is hot, but our roller is cold. So this means we deform them under stress. As soon as we deform them, we cool them down. And then now we're into the next stage. And the next stage is also containing the heating and cooling, but the temperature and the stress you involve in the second stage may be slightly adjust from the first one, because now you have different size of grain and different size of your strip, and so on and so forth. So you see, we have a much more degree of freedom, many more knobs to turn to optimize our microstructure. So to give us a better performance, but more than that, the whole thing can be a continuous process. So this process are designed to both reduce the complexity of the manufacturing as well as improving the magnet performance. So this is how we can convince the judges that we are one of the really innovative innovation of year 2023. So we win that R&D 100 award. So here is just one of the screenshot of we heat it up with an induction heater and then put it into this cold roller. The cold roller was coated with vinyl nitride. And here I show a picture of a strip magnet. So here is what we have. It's still, I think it's still considered as the best of magnet we get. And recently we make another one that is better than this. So it shows on the left, that's the MH curve. The gray one, that's the feedstock that's made of MGOe powder. You can see it is anisotropic. So after process, literally this is just a few minutes of process. We immediately can get a magnet that is with MH curve shown as green. The energy product is about 37.6 MGOe. So for the people in the field of permanent magnets, you can tell this MH curve is not ideal. We would really like to be really sharp and square. So this is one of the things that we are working on. So if we can do that, this thing can be 42, 43 MGOe. So this is the part that we really happy about, because think about it, the magnets typically require hours, if not days, to make. And then for us, it's just a few minutes we can fabricate this, and not to mention its high temperature stability. I will spend the rest of the 10 minutes to talk about all the research direction, because pretty much you can think that we are opening up a whole new research direction, a whole new platform for making magnets. Compared to the classic sintering magnet, which has been made near perfect in the past 30, 40 years. We only have 2 to 3 years to go this far. There's a lot of parameters, a lot of issues that appear to be more and faster than we can solve them. So typical factor and major factor are, for example, temperature and stress. What temperature do you do? What stress do you do? And what kind of combination? And of course, the major headache is the feedstock powder. You need to make sure they are all nanograins. Composition has to be uniform. And then the process-wise, how much is the reduction ratio per pass, roller size. And the casing material turned out to be a critical material, critical factor to consider. In fact, vacuum, we know vacuum is good now. Previously, we did not consider that. And post-annealing, and of course, it's time to introduce the grain boundary modifier, which can help us gain more coercivity. So I will go through for a few more examples until we run out of time. So the first one we care the most is the feedstock powder. The one that we use is MGOe made by Magna Quench. So this is the classic powder people use for hot press magnet. We realize this feedstock powder is not really nanograin. The majority is nanograin, like one is shown in the figure B, lower right. But on the upper right, you see there are periodically larger grains, few hundred nanometer of grains, and that pre-exists in the feedstock powder. We have not processing it. This already has this big grain. So we have a few hypotheses where this big grain come from. One of the things we think is come from the melt spinning process. There is a wheel side. There is this ribbon touching the wheel where you pull the material, the fastest one. So that's one on nano. But there is also free side one where your ribbon didn't touch the wheel. The ribbon actually facing the chamber. So that's the part where you have slightly slower cooling rate, where maybe you have formed the grain seed prior to other one, and then later on you grow into a bigger grain. So this is a running hypothesis. Of course, if you have this different grain size, when you heat it up, they all grow differently. You see 740, 760, 780, all of them are heated at this temperature for 15 minutes. We want to see at what temperature things start to getting out of control. So it seems like at 780, it's still okay. The grain size does not change much, even you have all these big grains. But starting 800 degrees C, you start to see suddenly much bigger grain size. That means some of the grains growth start to accelerate. And 820 and 840 things start to really out of control. So this just means that for us, our processing temperature should not be more than 800 degrees C, but this is the upper limit because we have not considered the effect of stress on aiding the grain growth yet. Temperature alone, we know 780 C for this particular set of powder. That's our top limit. So the strategy for this processing, as I mentioned before, is we are trying to balance the grain growth and also the texture. So you want grain to grow under the bias of stress so that we can form texture. So that means you want higher temperature. But on the other hand, you don't want your grain to grow too big because you will lose your coercive. That means you want lower temperature. So there has to be something in between that to give you the best texture, yet give you the smallest grain size that you can have. So one thing that we think that how about naturally, if you want the texture more, you introduce stress, right? So you want deformation as much as possible, and you want the deformation at the temperature as low as possible. And time-wise, you want to the whole exposure to this temperature stress to be as short as possible. That's the overall high-level principle that we think we should obey. But in reality, things are always different. It's not exactly like that. For example, we find it out this green MH curve, this is a process back at 760 degrees C. So it's the lowest temperature, right? Lowest temperature is supposed to have the highest coercivity, but yet its coercivity is less than the one that processes at the higher temperature at 780. Of course, by the time you go to 800 degrees, your temperature is so high, you completely lost your coercivity. We understand that part. But where it is 760, the coercivity comes from. Why you are lower? Shouldn't you be higher? So this is one of the things that puzzled us, and this is not a isolated event. So we consistently see those things. So now we have to consider a bigger picture instead of only the temperature. We think we also need to consider the effect of stress. So here it just shows that grain grows and the starting grain grow and the activation energy temperature, and also this factor N. This factor N actually corresponding to the stress of the situation. So if you apply stress, same temperature, your grain growth is going to be significantly accelerated. So that means that although the temperature we process the material is lower, the stress perhaps is higher. That's how at the end we actually end up with accelerated grain growth versus controlled. Here is another hypothesis, not hypothesis, actually observation. So it turned out that this 850 at the higher temperature, the processing load actually is less. So for the lower temperature, 800 degrees, you see for the same tube thickness when you press them, the stress actually, the load actually is higher. It's in a way it's intuitive because your tube is just more rigid at lower temperature and require higher stress to deform. So now we see this is a balance of temperature and stress. So another thing that we need to understand is the process has to be less aggressive. You need the grain need time and stress and temperature, all of them to grow. So when the temperature and stress is right, the grain still need a few seconds to grow under the bias of stress. Here, I just show that if we do it very aggressively with each time when we press them, we press it 37%. And in 3 runs, we complete the whole reduction. That's a blue curve. You see the texture development is not as good as the blue one, which we instead of 3 runs, we complete the whole deformation. We complete the whole thing in 4 runs. So each run is a bit less aggressive. So you can imagine if we do 5 runs, 6 runs, 7 runs, things should be getting better and better, right? So we studied that, but the story is actually is not completely true. There is also a limit. So due to the time, I have 2 minutes left, so I want to skip all these things and then go to a high-level conclusion. So here I just show you that across all the grain processed materials, the grains actually turn out to be not too bad. Their distribution is rather uniform. Oh, so let's see if I can. Just give me a second.
Whether you realize it or not, magnets are an important part of our everyday life. They're using electric vehicles, wind turbines, whether you realize it or not.
Okay, Cynthia, can you hear Ikena's voice?
Yes.
Very good, thank you. Oops.
Whether you realize it or not, magnets are an important part of our everyday life. They are using electric vehicles, wind turbines, spacecraft, and even our cell phones. These aren't just fringe magnets, though. These magnets need to be incredibly strong. Since the 1990s, the clear winner for these important applications was a neodymium-iron-boron based magnet with dysprosium. The dysprosium was an important addition because it made the magnet stronger with the ability to resist demagnetization and withstand hot temperatures. These magnets work well until recent years when dysprosium became difficult to obtain. In fact, the United States Department of Energy listed as a critical material. Rather than relying on dysprosium to strengthen magnet, scientists discovered another technique. Using high temperatures, they could create nanograin magnets. These function at temperatures as high as 180 degrees Celsius, almost the same as the original dysprosium-containing magnets. Unfortunately, nanograin magnets are expensive to make. The two-step batch process requires twice the tools and large vacuum furnaces, and there are limitations to product size, shape, and productivity. My name is Neodymium-iron-boron, and I am a scientist at the U.S. Department of Energy's Critical Materials Institute. Along with my colleagues at Ames Lab, we invented the continuous hot roll process to manufacture nanograin magnets. We sought to create an affordable high-temperature magnet without the need for dysprosium. In our process, a metal tube is filled with neodymium-iron-boron flakes. The tube greatly simplifies the vacuum sealing process because the space is much smaller and takes significantly less time to vacuum, minutes compared to hours. The use of the flame also eliminates the second step in the original nanograin process. Once the tube is sealed, it goes through the rollers, forming the final product. Induction coils between the rollers keep everything at optimum temperature. This results in more than 10 times as much nanograin magnet compared to the original batch process nanograin magnets. Our final product is less likely to require extensive machining to achieve manufacturers' desired shape. And in hot roll process eliminates the need for expensive vacuum furnaces. And dysprosium, which is hard to obtain, our method also moves to a continuous operation, dramatically improving productivity, which will make our process easier to scale. Importantly, our new magnets made with the hot roll process are extremely strong and can be very small, opening the door to new opportunities for these tried and true magnets.
All right, that's the end of my presentation. Any questions? All right, so I see first question. So the question is, the density is 7.4 gram per cubic centimeter. How can you increase density like in sinter magnet of 7.8? So Cynthia, people can hear me, right, Cynthia?
Yes, we can hear you.
Yes. Sintering, relying on sintering phase, liquid phase to fill in all these porosities. During the sintering process, magnet shrinks. Can be as bad as 15 to 20% even. So, but during our hard roll process, we compress in a way, this is not exactly a right way to say it, but you can think about it hot isopress. So we press everything, we fill in all the holes. And while we are doing that, the grains are growing under the bias stress. That's how we gain the texture. Does that answer your question? I'm not sure if I hear that. So I'm going to the next question. I hope I answered the first
next question.
All right, the next question. Next question is the hot rolling operation in open air. The question is yes, you do need to seal all your powder in a vessel. It could be tube, it could be a pouch, it could be a block, and then you just load your powder in and then seal it. After you seal your powder, protect it from the air, and then you can do whatever in air, or yeah, you can do that in air. All right. So, hey, John, how ductile are the hard road strip? The question is, how ductile are the hard road strip? Can you form them into radially oriented ring shape? It's with limited ductility. It's not, you can bend them to a certain degree, but it's not really that ductile. What you can do, John, is you can introduce a slight speed difference between the two rollers, and you can directly roll them into a curved shape. And then you can design the rolling process so that you can directly produce them into a curved magnet. Hope that answered your question. Next question is from Andrew. Are you degassing the powder or just high vacuum? So far, we did not degas our powder. We store powder, everything in glove box. We don't think that it has much moisture or anything, but we do realize that baking the powder in vacuum might be helpful. We did one brief run, didn't see a significant effect. This does not mean that's just the end of the story. Vacuum wise, we don't need to pull too high a vacuum, just pull some of the vacuum is good enough. So what is the temperature of the wheel? The temperature of the wheel is keep cold, room temperature. We don't heat them. Actually, as a matter of fact, we would like it to be cold. Next question, Chad. What other deformation method did you consider? Rolling is efficient and scalable, but not on the way to consider deformed powders. Correct. So far, we only consider the rolling. The main reason is we think this is could be a continuous process, significantly increase our productivity. They have not considered any other deformation method like extrusion, because if you do the extrusion, the whole die, the pricing, and I'm not sure if you can load the powder, the tube continuously to achieve a semi-continuous process. There is another question asked us to try extrusion. I think I just explained. Extrusion give you a pretty good texture, but you see extrusion, you have to press to the end. That means you cannot really do a really long feedstock. That immediately limits your productivity and process. We think the rolling is the most friendly to scale up. What is the mechanical property compared to the commercial neo? This is a very, very sharp question. Actually, if we peel off our casing, and then the material actually is already during the peeling, you already introduce a micro crack to the magnet. So the magnet is even worse than the commercial neo magnet. Commercial neo magnet is brittle, but you still can handle it. You still can throw it on the table. It won't fracture by itself. Of course, if you really abuse it, it will fall apart. But for our magnet, if you peel the case, the protection case in the sleeve, it will be worse than the commercial neo magnet. On the other hand, if you don't peel your case, you'll keep it as a protection later. Actually, your magnet can be held there, and it's very strong. Actually, it's a protection.
Your attention, please. Your attention, please.
Oops, sorry about.
The tornado watch has been issued for Story County.
We
until
have a
10
tornado
p.m.
watch here.
Please be alert.
Uh-oh.
Take immediate shelter if a warning is issued. Your attention, please. Your attention, please.
There
The
go.
tornado watch has been issued for Story County until 10 p.m. Please be alert for threatening weather and be prepared to
Okay.
take.
The answer is
immediate shelter
pay
if a
attention.
warning
It's
is
not a
issued.
real warning
Thank
yet.
you.
So I was saying that if you have casing, you can provide a mechanical protection, also corrosion protection. But the issue is you are adding a layer. You're adding a layer of material in between your magnet and the end use, and that layer take away your air gap, and it could be an issue. So that layer has to be really thin. We are actually working on it to find a way to really reduce this casing layer. Hope that answer your question. That's a very good question, actually. Without casing, our material, because the way we're processing it, the material you can imagine is being not naturally sintered. We are pressing them, we are deforming them. There's a lot of stress, a lot of metal crack in it. Next question from Aaron. Given the high degree of deformation, residual stress and dislocation density, have you observed any recrystalline influence the resulting texture mixture, or is it only undergoing recovery? This is very good. I was about to answer this. Yes. Post heat treatment should get rid of all the stress. And we actually you would assume, Aaron, that doing a little bit of heat treatment to all this hot deformed magnet, it will get rid of heat stress. It will further kind of smooth your grain boundary, get your coercivity up, and make your magnet better, right? But actually, we did two types of tests on this, two types of study on this. One is without the grain boundary modifier. The other one is just the MQF. The MQF one, after you do the annealing, actually get material worse, much worse. I think there is a significant grain recrystallization going on that causes the grain to grow out of control. But on the other hand, if we use the precision copper aluminum, that type of grain boundary modifier, and we do find post-heat treatment can, how much? I think almost 15% improvement of our coercivity. Just a few 400 degrees C, half hour heat treatment will really help us. So the answer to your question is actually depends, depending on what is the material that we treated. All right. So there is no more open questions left.
It looks like we don't have any more open questions, but we do have a little bit of time. If anybody would like to post another question. In the meantime, I'd like to thank you for such a great presentation on hot roll neomagnets, the advantages, and again, how important magnets are to our energy and vehicle efficiencies as well. So thank you again for a great presentation. And if, while we're waiting for any other questions here, does it look like anything is coming up? Then I am going to put up our very, very last slide. And this is a reminder that we do this series monthly, and that's interesting. We want to thank you for participating in this one. We will have a webinar again this upcoming month, and it is with Remade, and we're going to learn all about that organization. And what I am going to do at this point is check again for a couple of slides. And if we do not have anything, we're going to end this webinar. Any additional questions?
Was that last question answered?
Let's see. Do we have one yet one question? Do you see that, Junkui?
Let me see. I was struggling with sorry. Okay. Oh, there's one more. Oh, yes, it says that you stated the reduced dependence on heavy rare earths. Have you achieved this? No. No, not yet. But if we can show our nanograin magnet can be used at a higher temperature without heavy rare earths, I think it's just a matter of time that we can do that. That's for us. But if you look at the magnet itself currently being produced by Daido, which they already have a commercial product of this nanograin, is just not hot rolled, the traditional one. It can already replace magnet that containing with heavy rare earths, but it's just the cost wise perhaps is not feasible at this moment. And this cost is what we are trying to address. All right.
Thank you for attending. This recording is going to be available next week at ameslab.gov/CMI and or on the YouTube Innovation Hub channel. Please join us for the next webinar on May 21st to learn about Remade with the CEO, Magda Azer. Soon there are going to be details in the critical times. And if you have suggestion for a future webinar topic, please do not hesitate to join us.
Déjame, ya voy saliendo. Ay, guau.